Have you ever stared at the night sky and wondered what existed before everything began? Before galaxies, before stars, before even time itself? It's the kind of question that makes your brain feel like it's doing gymnastics while blindfolded. And here's the thing that might keep you awake tonight. Scientists have actually found some pretty strange evidence about what might have happened before our universe even existed. Now, I should warn you up front. This video might be so mind-bending that you'll find yourself questioning everything you thought you knew about reality. But if that happens, at least you'll walk away with some seriously impressive cosmic knowledge to ponder while you're lying there at 3 a.m, wondering if we're all just living inside a black hole. Before we dive into this cosmic rabbit hole, I'd love to know where in the world you're watching from and what time it is for you right now. Are you in London at midnight, contemplating existence? Maybe it's dawn in Tokyo and you're having an early morning existential crisis? Drop a comment and let me know there's something beautifully ironic about people scattered across space-time discussing what came before space-time even existed. If you find these kinds of mind-expanding journeys as fascinating as I do, please consider hitting that like button and subscribing. It genuinely helps more curious minds like yours discover these cosmic mysteries. And trust me, we're just getting started on this wild ride through the strangest ideas in modern physics. So, here's what I'm about to reveal. Scientists haven't just been sitting around shrugging their shoulders at this impossible question. They've developed some absolutely bizarre theories backed by real mathematics and evidence that suggest our universe might not be the beginning of everything after all. We're talking about ideas so strange they make science fiction look tame mirror universes running backward in time, infinite cycles of cosmic death and rebirth, and the possibility that our entire reality emerged from literally nothing through quantum mechanics. What you're about to discover isn't just theoretical speculation. This is cutting-edge science from Nobel Prize winners, renowned physicists, and brilliant minds who've dedicated their lives to unraveling the deepest mysteries of existence. And some of their conclusions are going to absolutely blow your mind. Let's start with perhaps the most unsettling realization that scientists have come to about this question. For most of human history, asking what came before the universe seemed perfectly reasonable. After all, everything has a beginning, right? But according to some of the brightest minds in physics, this question might be fundamentally meaningless, like asking what's north of the North Pole or what color is the number 7. This isn't just philosophical wordplay. When Albert Einstein developed his theory of general relativity in the early 1900 seconds, the mathematics led to a startling conclusion. Time itself came into existence with the universe. Stephen Hawking, one of the most celebrated physicists of our time, put it brilliantly when he said that asking what happened before the Big Bang is like asking what lies north of the North Pole. The question itself breaks down because there is no before when time doesn't exist. But here's where it gets really weird. Even though the question might be technically meaningless, scientists have kept pushing at it anyway, and what they've discovered is far stranger than anyone expected. Let me tell you about cosmic inflation, a theory that's completely rewritten our understanding of the universe's beginning. Picture this. Before the Big Bang as we typically imagine it, something absolutely mind-boggling happened. The universe underwent a period of expansion so rapid and so extreme that it doubled in size at least 80 times in less than a trillionth of a trillionth of a trillionth of a second. I know that sounds like science fiction, but this isn't speculation. The evidence for cosmic inflation comes from the cosmic microwave background radiation, essentially the afterglow of the Big Bang that we can still detect today. When scientists mapped this radiation using satellites like the Planck mission, they found tiny fluctuations in temperature that match exactly what inflationary theory predicted. It's like finding a fingerprint from the universe's earliest moments. But here's the kicker. If cosmic inflation is real, it completely changes what we mean when we talk about the beginning. The hot, dense state we call the Big Bang wasn't actually the beginning, it was more like a cosmic phase transition. Before the Big Bang, according to this theory, the universe was cold, empty, and expanding at an unimaginable rate due to a mysterious form of energy that permeated empty space itself. Alan Guth, one of the pioneers of inflationary theory, had what he later called his spectacular realization on the 7th of December, 1000, 979. He figured out that this period of exponential expansion could explain why our universe has all the specific properties we observe today. But his theory opened up an even bigger can of worms. You see, if inflation happened once, what's to stop it from happening again, and again, and again? This leads to what scientists call eternal inflation, the idea that somewhere out there in the vast cosmic landscape, inflation is still happening. New regions of space are constantly inflating, creating what physicists call pocket universes. Our entire observable universe, with its hundreds of billions of galaxies, might be just one tiny bubble in an infinite cosmic foam. This isn't just wild theorizing. MIT's Alan Guth has said, "It's hard to build models of inflation that don't lead to a multiverse." Most inflationary models naturally produce an infinite number of universes, each with potentially different physical laws, different constants of nature, and different possibilities for the evolution of complexity in life. But wait, it gets even weirder. Some scientists have proposed that our universe isn't just one bubble in an infinite multiverse. Instead, they suggest we might be living inside a black hole. Yes, you heard that right. According to this hypothesis, every time a black hole forms in our universe, it creates a new universe on the inside. From our perspective, matter and energy disappear into the black hole, but from the perspective of that matter, it emerges into a new, expanding universe. This creates a nested hierarchy of realities that's almost too strange to contemplate. If this theory is correct, our entire cosmos, everything we can see, from the smallest particles to the largest galactic superclusters, exists within a black hole in some parent universe. And every black hole in our universe contains its own complete cosmos with its own physics, its own galaxies, and potentially its own forms of life, wondering about what came before their universe. The mathematics behind this idea come from studying what happens at the center of black holes, where Einstein's equations predict a singularity, a point where density becomes infinite, and the normal rules of physics break down. Some physicists suggest that instead of a singularity, there might be a kind of cosmic bounce that creates a new expanding universe on the other side of the black hole. Speaking of bounces, that brings us to another mind-bending possibility. What if our universe didn't begin with a bang, but with a bounce? According to cyclic cosmology models, the universe goes through infinite cycles of expansion and contraction. In this scenario, what we call the Big Bang was actually a big bounce, the moment when a previous contracting universe reached its minimum size and began expanding again. This idea has ancient roots. Medieval philosophers in India taught that the universe goes through endless cycles of creation and destruction. Now, some modern scientists have arrived at remarkably similar conclusions using advanced mathematics and quantum mechanics. The theory suggests that instead of emerging from nothing, our universe emerged from the collapse of a previous cosmic epoch. But perhaps the strangest recent development comes from Nobel Prize winner Roger Penrose, who's proposed something called Conformal cyclic cosmology. According to Penrose, our universe isn't just one cycle in an infinite sequence, it's one aeon in a cosmic story that has no beginning and no end. Each aeon begins with what we experience as a Big Bang, and ends in the far distant future when the universe has expanded and cooled to the point where only massless particles remain. Here's the truly bizarre part. Penrose claims that the end of each aeon somehow becomes the beginning of the next through a mathematical transformation. The infinite future of one universe becomes the Big Bang of the next, creating an eternal cycle where the universe dies and is reborn over and over again, each time carrying subtle imprints from the previous cycle. And if you think that's as strange as it gets, we haven't even talked about the mirror universe yet. Now, the mirror universe theory might be the most elegant and unsettling idea we've encountered so far. Imagine this. When our universe began, it didn't emerge alone. Instead, physicist Neil Turok from the Perimeter Institute suggests that the Big Bang created two universes simultaneously ours, and a mirror universe composed of antimatter where time flows backward. Picture two shuttlecocks arranged cork to cork, forming an hourglass shape with time flowing in opposite directions. While we experience time moving forward from past to future, this mirror universe experiences time moving from what we'd call future to past. It's not just that events happen in reverse. The fundamental arrow of time itself points the opposite way. What makes this theory particularly fascinating is how it emerges from something called CPT-symmetry, a fundamental principle in physics that suggests nature has a built-in mirror that simultaneously reflects matter and antimatter, left and right, and forward and backward in time. If this symmetry is truly fundamental, then our universe existing alone would actually violate these deep principles of physics. The implications are staggering. Every moment you're living right now, there might be an antimatter version of you in that mirror universe experiencing the same moment, but with time flowing in the opposite direction. It's like having a cosmic twin who exists in a reality where cause and effect work completely backward from our perspective. But here's what makes this more than just philosophical speculation. This mirror universe model provides a potential explanation for dark matter. You know, that mysterious stuff that makes up about 27% of our universe but refuses to interact with light or normal matter in ways we can easily detect. According to Turok and his colleagues, dark matter might actually be particles that are somehow connected to or influenced by this mirror universe. The beauty of this theory lies in its simplicity. Instead of requiring exotic new physics or infinite multiverses, it suggests that the fundamental symmetries we already know about in nature might demand the existence of this cosmic mirror. It's as if the universe couldn't exist any other way without breaking its own deepest rules. Now, while we're talking about dark matter, let me blow your mind with another recent discovery. Scientists have traditionally assumed that dark matter formed after the Big Bang, during the hot, dense conditions of the early universe. But new research suggests something far more radical. Dark matter might have formed before the Big Bang even happened. Researchers from the University of Texas at Austin have developed what they call the warm inflation via ultraviolet freeze-in model. I know, scientists really need to work on their naming conventions. But the idea behind this tongue-twisting title is revolutionary. They propose that during the inflationary period, remember, that's the exponential expansion that happened before the conventional Big Bang, the extreme conditions could have created dark matter particles through tiny quantum interactions. Most models assume that anything formed during inflation would be obliterated by the universe's rapid expansion. It's like trying to build a sandcastle while someone's pointing a fire hose at the beach. But this new model suggests that dark matter not only survived inflation, it thrived during it, becoming one of the universe's earliest building blocks. If this is true, then dark matter has been shaping the cosmos for far longer than we ever imagined. It would mean that this mysterious substance was already there, waiting in the wings, when our universe made its dramatic entrance onto the cosmic stage. But let's step back for a moment and consider what might be the most radical approach to this whole question. Stephen Hawking, in one of his final theoretical works, developed something called the no-boundary proposal with James Hartle. This isn't just another theory about what came before the universe, it's a theory that suggests the question itself is based on a fundamental misunderstanding of how reality works. According to the no-boundary proposal, the universe doesn't have a beginning in the way we normally think about beginnings. Instead, it emerged from what physicists call a quantum state, where the normal rules of cause and effect don't apply. It's like asking what's south of the South Pole once you reach the southernmost point on Earth. The concept of south simply doesn't make sense anymore. Hawking used this analogy deliberately. He suggested that if you trace the history of the universe backward in time, you eventually reach a point where time itself becomes meaningless, just like directions become meaningless at the poles. The universe doesn't have an edge or boundary in time any more than Earth has an edge in space when you travel around its surface. This proposal relies on some seriously advanced mathematics involving something called imaginary time, and no, that doesn't mean pretend time. In quantum mechanics, imaginary numbers are real mathematical tools that help describe how particles behave at the smallest scales. When Hawking and Hartle applied these concepts to the entire universe, they found solutions where the cosmos could emerge spontaneously from a quantum state without requiring anything to exist beforehand. The mathematics suggests that the universe could literally create itself from nothing through quantum processes that we're only beginning to understand. It's like the ultimate magic trick, except instead of pulling a rabbit out of a hat, quantum mechanics might pull an entire universe out of the void. But here's the catch. The no-boundary proposal has faced serious mathematical challenges. Recent work by physicists like Neil Turok has pointed out problems with the theory's stability. The original calculations seem to predict that the universe should be wildly chaotic and non-uniform, which clearly doesn't match the relatively smooth and orderly cosmos we actually observe. However, just when it seemed like the no-boundary proposal might be dead in the water, other physicists have found ways to modify the theory to address these problems. They've shown that by adjusting the mathematical framework, you can get stable solutions that do predict a universe like the one we see around us. This back and forth highlights something crucial about science at the cutting edge. These aren't settled questions with neat, tidy answers. We're dealing with ideas so fundamental and so far beyond our everyday experience that even the greatest minds in physics disagree about which approaches might be correct. What's remarkable is that all these theories, cosmic inflation, mirror universes, cyclic cosmologies, the no-boundary proposal, make testable predictions. Scientists are actively looking for evidence that could support or rule out these ideas. They're studying the cosmic microwave background radiation for subtle patterns that might reveal signs of previous cosmic cycles. They're analyzing the distribution of galaxies for hints of extra dimensions or mirror matter. They're building gravitational wave detectors that might be sensitive enough to detect echoes from before the Big Bang. Roger Penrose, the Nobel Prize-winning physicist behind Conformal cyclic cosmology, claims he's already found evidence in the cosmic microwave background of events that happened in previous cosmic cycles. He points to unusual circular patterns in the radiation that he says are the signatures of massive black hole collisions from a previous aeon. Most other cosmologists remain skeptical of these claims. They argue that the patterns Penrose identifies could easily be explained by random fluctuations or instrumental effects. But the fact that we can even look for such evidence shows how far our understanding has advanced. What's truly mind-bending is that some of these theories suggest we might be able to observe the consequences of what happened before our universe began. If Penrose is right, then every time we look at a detailed map of the cosmic microwave background, we're seeing ghostly imprints of a previous cosmic epoch. If the mirror universe theory is correct, then dark matter interactions might give us glimpses into that backward-flowing realm of antimatter and reverse causality. And here's what might be the strangest possibility of all. What if multiple theories are simultaneously correct? What if our universe emerged from a quantum state through the no-boundary proposal, underwent eternal inflation that created a vast multiverse, exists as part of an infinite cycle of cosmic death and rebirth, and is paired with a mirror universe running backward in time? The mathematics of modern physics suggests that reality might be far more layered and complex than our everyday experience suggests. We might be living in a cosmos that's simultaneously emerging from quantum nothingness, inflating into infinite multiverses, cycling through eternal phases, and mirrored by backward-flowing time. It's enough to make you wonder whether the question what came before the universe even scratches the surface of how strange existence really island. But here's where things get even more mind-bending. What if I told you that some of the most brilliant scientists alive today think our entire understanding of before and after might be fundamentally wrong? What if time itself isn't what we think it is? Enter string theory, the mathematical framework that attempts to describe all fundamental forces and particles as tiny vibrating strings in higher dimensional space. According to string theorists, our familiar 3 dimensions of space and 1 dimension of time might be just a slice of a much larger reality containing up to 11 dimensions. In this higher dimensional landscape, the rules change completely. Events that seem impossible in our 4-dimensional space-time become not just possible, but inevitable. The Big Bang might not be a singular event, but rather one of countless branes, higher dimensional surfaces colliding in this vast cosmic space. Picture two enormous sheets floating through higher dimensional space, each representing an entire universe. When these sheets collide, the impact creates what we experience as the Big Bang. But from the perspective of these higher dimensions, it's just another collision in an ongoing cosmic dance that's been happening forever. The mathematics behind this idea are staggering in their complexity, but they make specific predictions we can test. If our universe was born from such a collision, it should have left distinctive patterns in the cosmic microwave background radiation. Scientists are actively searching for these signatures right now, using some of the most sophisticated instruments ever built. What's particularly fascinating is how string theory handles the problem of time. In our everyday experience, time flows in one direction from past to future. But in the mathematical framework of string theory, time becomes just another coordinate, like north or south. The universe doesn't evolve through time so much as exist as a complete four-dimensional structure where all moments past, present and future are equally real. This leads to something called the block universe model, where what we call the present is just where our consciousness happens to be located in a vast four-dimensional landscape. Every moment that has ever happened or ever will happen exists simultaneously in this higher dimensional structure. If this is true, then asking what came before the universe is like asking what's to the left of a painting while you're looking at it from the front. The question assumes a perspective that doesn't capture the full reality of the situation. But string theory isn't the only game in town. Another approach called loop quantum gravity takes a radically different tack. Instead of adding extra dimensions, it suggests that space and time themselves are made of discrete quantum building blocks like pixels in the fabric of reality. According to loop quantum gravity, if you could zoom in far enough on any point in space, you'd eventually reach a scale where the smooth fabric of space-time breaks down into a foam-like structure of quantum fluctuations. At this scale, the normal rules of physics cease to apply, and reality becomes fundamentally probabilistic rather than deterministic. When loop quantum gravity theorists trace the universe backward to its beginning, something remarkable happens. Instead of hitting a singularity where density becomes infinite and physics breaks down, they find that the universe bounces at a finite size. The Big Bang becomes a big bounce, a transition from a previous contracting phase to our current expanding one. What makes this particularly intriguing is that loop quantum gravity makes it possible to trace what happened before the bounce. According to these models, our expanding universe emerged from a previous universe that was contracting. That universe might have been contracting for billions or even trillions of years before reaching the point where quantum effects caused it to bounce back into expansion. This creates a picture of cosmic evolution that's both cyclical and eternal. Universes expand, reach a maximum size, contract back down to a quantum bounce, then expand again. Each cycle might last hundreds of billions of years, with the bounce itself taking only a tiny fraction of a second. But here's what's really wild. Some versions of these bouncing universe models suggest that information can pass from one cycle to the next. The quantum fluctuations that cause the bounce might preserve certain patterns or structures from the previous universe, carrying them forward into the new expansion phase. If this is correct, then the large-scale structure of our universe, the distribution of galaxies, the properties of dark matter, even the fundamental constants of physics might be echoes of events that happened in a previous cosmic cycle that ended trillions of years ago. Meanwhile, other physicists have been exploring what might be the most radical possibility yet, that the universe is computational in nature. According to digital physics, reality might be fundamentally composed of information rather than matter and energy. In this view, what we call particles, forces, and space-time are all emergent properties of underlying computational processes. The universe is essentially running a vast program, with the laws of physics being the code that governs how information is processed and transformed. This idea isn't as far-fetched as it might sound. We already know that quantum mechanics involves fundamental limits on information, the uncertainty principle, quantum entanglement, and the holographic principle all point to deep connections between physics and information theory. If the universe is indeed computational, then asking what came before it is like asking what existed before someone turned on a computer. The answer might be that the computational substrate, the underlying system capable of running the universe program, has always existed in some form. This leads to the possibility that our universe is just one of countless simulations running on some vast cosmic computer. Different programs might create universes with different physical laws, different dimensions, or different fundamental constants. What we experience as the history of the cosmos might be just one execution of an infinitely complex algorithm. The implications are staggering. If we're living in a simulation, then the question of what came before our universe might have a surprisingly mundane answer. Someone or something pressed the cosmic equivalent of a start button. But perhaps the most unsettling possibility is that we might never be able to definitively answer the question of what came before the universe. Not because we lack the intelligence or technology, but because the answer might be fundamentally unknowable given the structure of reality itself. This brings us to something called the cosmic censorship hypothesis, the idea that the universe protects us from observing certain types of extreme physics. Singularities, where the laws of physics break down, are always hidden inside black holes where we can't see them. The Big Bang singularity is hidden behind the cosmic event horizon. We can observe the universe back to a certain point, but not beyond. Some physicists suggest this might not be a bug in our understanding, it might be a feature. Perhaps the universe is structured in such a way that certain questions simply can't be answered by observers within it. The ultimate nature of reality might be forever beyond our reach, not due to practical limitations, but due to fundamental logical constraints. This connects to deep questions in mathematics and philosophy about self-reference and incompleteness. Just as mathematician Kurt Gödel showed that any sufficiently complex mathematical system contains truths that can't be proven within that system, it's possible that any universe complex enough to contain conscious observers also contains mysteries that those observers can never fully solve. If this is true, then the question what came before the universe might be unanswerable, not because we haven't found the right theory yet, but because finding the answer would require stepping outside the very framework of logic and causality that makes the question meaningful in the first place. Yet scientists continue pushing at these boundaries, driven by an almost compulsive need to understand. They're building more sensitive detectors, developing more sophisticated mathematical models, and conducting experiments at the very limits of what's technically possible. The Large Hadron Collider smashes particles together at energies that recreate conditions from the first moments after the Big Bang. Gravitational wave detectors like LIGO are sensitive enough to measure distortions in space-time smaller than 1,000th the width of a proton. The James Webb Space Telescope can peer so far into space that it's literally looking back in time toward the universe's beginning. Each new observation brings us closer to the ultimate questions. Every detected gravitational wave carries information about the nature of space-time itself. Every ancient galaxy observed by powerful telescopes tells us something about how structure formed in the early universe. Every particle collision at the LHC probes the fundamental nature of matter and energy. And sometimes, these observations reveal things that are completely unexpected. In 2016, the discovery of gravitational waves opened up an entirely new way of observing the universe. These ripples in space-time itself carry information about events that would be completely invisible to traditional telescopes. Some theoretical physicists believe that gravitational waves from the very early universe might still be propagating through space, carrying information about what happened during cosmic inflation or even before. If we could detect these primordial gravitational waves, we might finally have direct observational evidence of what the universe was like in its first moments. Stephen Hawking, in his final paper published just before his death, suggested that these primordial gravitational waves might be detectable by future generations of gravitational wave observatories. He proposed that the patterns in these waves could tell us whether we live in one universe, among many, or whether the multiverse theory needs to be abandoned in favor of something even stranger. The search for these cosmic fingerprints continues. Scientists are planning space-based gravitational wave detectors that would be millions of times more sensitive than current ground-based instruments. They're developing new theoretical frameworks that might reveal subtle signatures of pre-Big Bang physics in the cosmic microwave background radiation. But perhaps most intriguingly, they're beginning to realize that the answer to what came before the universe might not come from looking outward into space, but inward into the quantum realm. At the smallest scales of reality, where quantum mechanics reigns supreme, the normal rules of cause and effect break down completely. In the quantum world, particles can appear and disappear spontaneously. They can exist in multiple states simultaneously until observed. They can be instantaneously connected across vast distances through quantum entanglement. Most remarkably of all, the quantum vacuum empty space itself is seething with virtual particles that pop in and out of existence in accordance with the uncertainty principle. Some physicists believe that understanding these quantum processes at the deepest level might reveal how something as large and complex as an entire universe could emerge from nothing. The mathematics of quantum field theory already shows us that particles can be created from pure energy, and energy can be created from the curvature of space-time itself. If the universe began as a quantum fluctuation, a random burp in the quantum vacuum that happened to be large enough and stable enough to inflate into a full cosmos, then the question of what came before becomes meaningless. Quantum fluctuations don't have causes in the traditional sense. They simply happen, governed by probability rather than deterministic laws. This brings us full circle to one of the most profound realizations in modern physics. The universe might be fundamentally probabilistic rather than deterministic. What we experience as the solid, predictable reality of classical physics might be just the averaged-out behavior of countless quantum events, each of which is inherently random and unpredictable. If this is true, then the existence of the universe itself might be the result of an incredibly improbable but not impossible quantum event. In an infinite quantum multiverse, every possible fluctuation will eventually occur, including fluctuations large enough to create entire universes. From this perspective, we exist not because the universe was designed or created, but because in an infinite quantum multiverse, our existence was inevitable. Somewhere among the countless possible quantum fluctuations, there had to be one that resulted in a universe capable of supporting the complex chemistry needed for life and consciousness. The anthropic principle suggests that we observe the universe to have the properties it does, precisely because we exist to observe it. In a multiverse where different regions have different physical laws and constants, we necessarily find ourselves in a region compatible with our existence. This might explain why our universe seems so finely tuned for life. The strength of gravity, the mass of the electron, the rate of cosmic expansion, all these quantities appear to be perfectly calibrated to allow stars to form, heavy elements to be created, and complex molecules to assemble into living systems. Rather than requiring a cosmic designer, the anthropic principle suggests that this apparent fine-tuning is simply a selection effect. We observe a life-friendly universe because we couldn't exist in any other kind. But this raises yet another mind-bending possibility. What if consciousness itself plays a fundamental role in determining the nature of reality? Some interpretations of quantum mechanics suggest that observation is required to collapse quantum possibilities into definite outcomes. If this is true, then conscious observers might not just be passive witnesses to the universe's evolution, they might be active participants in determining what becomes real. This connects to some of the strangest ideas in theoretical physics about the relationship between mind and matter, observer and observed, consciousness and cosmos. Some physicists have seriously proposed that the universe might be fundamentally conscious, or that consciousness might be a basic feature of reality like mass or charge. If consciousness is indeed fundamental, then the question of what came before the universe might be intimately connected to the question of what consciousness is and how it relates to physical reality. The beginning of the universe might not just be about the emergence of matter and energy, but about the emergence of the capacity for experience itself. And that brings us to perhaps the most humbling realization of all. So here we are, having journeyed through some of the most mind-bending ideas in modern science, from quantum fluctuations creating universes out of nothing, to mirror realities running backward in time, to the possibility that we're all living inside a cosmic computer simulation. We've explored cosmic inflation, eternal multiverses, bouncing cosmologies, and the radical notion that time itself might be an illusion. What's remarkable is that these aren't just wild philosophical musings. These are serious scientific theories developed by Nobel Prize winners and leading physicists, backed by mathematics and actively being tested through observation and experiment. We're living through an incredible moment in human history where we can actually investigate what might have existed before existence itself. The strangest part? We might never have a definitive answer. The question, what came before the universe, might be fundamentally unanswerable, not because we're not smart enough, but because the answer might lie beyond the very framework of logic and causality that makes the question meaningful. But perhaps that's okay. Perhaps the real revelation isn't finding the ultimate answer, but discovering just how beautifully strange and layered reality might be. Whether we're floating in an infinite multiverse, cycling through eternal cosmic phases, or emerging spontaneously from quantum nothingness, we're part of something far more magnificent and mysterious than our everyday experience suggests. So the next time you look up at the night sky, remember, you're not just seeing distant stars. You might be glimpsing echoes of previous cosmic cycles, shadows of mirror universes, or the edge of an infinite multiverse where every possibility becomes reality. Thanks for taking this incredible journey with me. If this video has left your mind properly twisted, hit that like button and subscribe for more cosmic mysteries that'll keep you wondering about the nature of everything. And let me know in the comments, which of these theories do you find most mind-bending? Sweet dreams, and remember, reality is far stranger than we ever imagined.